recording. So we're not going to use, in this class, we're never going to use 6.02 times 10 to the 23 anymore. That number's gone. All right? This is physical chemistry. We should use the precision that is given to us. And thankfully, the International Union of Applied and, well, it's actually this SI, it's a big multinational conglomerate of scientists that come up with the definitions of the constants and their values and their errors if they're not defined exactly. And Avogadro's number now, in 2024, is defined exactly. It has 0 error. It's a perfect number. It's defined to be fixed. So we can always define a mole as an exact amount of particles. And that number is 6.02214076 times 10 to the 23. Okay? So it has something like 9 significant digits. This number is defined exactly. It's just a definition. So probably when you learned chemistry, this number was never specified to be exact. In fact, when I was your age, it wasn't defined exactly. It was replaced with an exact number in 2018. But this is exactly what Avogadro's number is. There's no more digits to it. There's no error. It has 0 error. Okay? This is the number we'll use. Now, in this class, we won't need to use all of these digits. Right? There's very few problems where we'll need all of them. However, you'll certainly need to, maybe it would be better to think about this as 6.0221. Right? We'll talk about where a good place to cut that off is. All right? That's going to be a discussion for this class. Is what's an appropriate amount of units to use in your problem? Okay, we'll talk about that next week. What are some other properties of these particles that we can measure about them? Is there anything else intrinsic about these particles that we could maybe measure? I mean, think about them as balls. Right? They're just little spherical balls. Right? What are some things that balls have? Say it again?
Mass.
Yeah, mass. Exactly. Right? So let's do mass. Right? This seems really trivial, but it's important that we think about these things. Right? Our next variable is mass. Sorry, let me be more consistent with my writing. So this is our first one. Our second one is mass, which sometimes we write as m, lowercase m. Sometimes we write molar mass, which is uppercase M. Okay. All right. You'll sometimes see me use big M and little m. Little m means the mass of a single particle. Big M means a mass of a mole of particles. Okay. Right. And of course, what are the units? What are the units for mass? Simple question.
Grams.
What's that?
Grams.
That's not the official unit of mass.
Kilograms.
Kilograms. Be very careful with that. So it's important that we're going to define everything in SI units. We're going to have a lot of constants and things that numbers we're going to have to work with. Make sure that you convert everything to kilograms or kilograms per mole, right? Right? Kilograms. Or kg per mole. It's up to you. Whatever you prefer. Okay? We're sometimes going to interchange between these two. Sometimes we're going to talk about a single particle, right? Kilograms per mole is not a particularly useful unit for that, because one atom doesn't weigh anything near a kilogram, right? But a kilogram per mole, the number of kilograms in a mole is much closer to a kilogram. Right? So that's another unit. Another unit we like to use is AMU, atomic mass units. So AMU stands for atomic mass units. And it's defined kind of arbitrarily, but I'll do a conversion for you. So the mass of, it's roughly defined to be the average mass of the hydrogen atom, but it's not exactly the average mass of the hydrogen atom. Let me get the exact number. So 1 AMU turns out to be, let me just get it. I always forget. I'll start my thinking. There we go. 1.66054 times 10 to the minus 27 kilograms, right? And this is roughly the mass of a hydrogen atom, okay? Hydrogen's a little bigger. It's 1.007 AMU, right? But the average mass of hydrogen is assumed to be about 1, right? And this is the mass of a hydrogen atom, okay? All right, that's a very useful number. There's another term that we use for this that's more biochemical. Biologists use this number, this unit. It's the same unit. It's called a Dalton, a DA. Maybe you've heard of Daltons before. Mass spec uses Daltons a lot. It's the same concept, right? 1 Dalton is a hydrogen. Okay. So we'll interchange between these units a lot because it's contextual. Sometimes it's really useful to talk about, in physics, to talk about kilograms because that's the SI unit for mass, right? If you talk about energy or momentum or any sort of property in physics, we use kilograms. But in chemistry, we use kilograms per mole because we rarely deal with one atom. But when we do, we often use AMU as an alternative unit. Okay? You'll see me interchange between these, and it's good to get comfortable with them. Okay, so we have 2 variables about the material that we put in there. All right? And that's all we need right now. All right? Of course, you might say, okay, well, they might be carbons, or they might be oxygens, but the only difference between a carbon and oxygen in this case right now is that they have different masses. You may also ask, well, atoms may also have a volume, right? They're spheres. They have to have some definite size, okay? So remember that in the back of your head. We're not going to worry about that right now. We're going to assume that these balls are basically little point masses, just tiny little infinitesimally small balls that have mass in them, okay? We'll come back to the idea of them having a shape in a couple weeks. Right? We don't want to worry about that. I want to create as simple of a model as possible, right? This is our spherical cal, as the physicists would like to call it. Okay, so let's think about some other things we can talk about in this box. What are some other things that we can measure? And again, I'm talking like kindergarten level here, right? Very, very simple ideas, right? So we have particle number, we have the mass of those particles. What are some other properties of the box we can measure? Can you say anything about the box? Yeah, what do you call that more specifically? What's the volume of the box? Yeah, volume it turned out to be an extremely important variable here. And you'll see why very quickly. So we can measure the volume of the box. Right, so the second step, what we're going to do is we're going to fill this box with countable material. The second step is we're going to define a volume. So our variable is V for volume. What are the units for volume? Good question, huh? Some units for volume. You go buy a bottle of liquor at the store, what's the unit you use when you buy the liquor? Liters. Liters, there we go. I know someone knew that out here. Right? Does anyone know what the metric version of liters are? Because liters not a meat, right? It has nothing to do with meters. Does anyone know what a liter is? It's not meters cubed. It's not. It's interesting, isn't it?
Well, centimeters is milliliters.
That's right. Right. So centimeter. So let's stop for a second, Monica, and you got the good point. So let's be very careful here. So liters is a good number to use. It's very convenient for us, but it's not the official SI unit. Okay, a liter. So as Monica said, we have a couple different units, and it's all contextual, right? Units are always contextual. We always pick units that are useful to talk, right? Because it's not reasonable to think about volume in terms of fractions of an earth, for instance, right? That's a dumb number, right? So we use them contextually. But when we're going to do calculations, we want to make sure that we can always put things in the real SI units. Because when you start to compute things with constants, the speed of light, for instance, or Avogadro's number and things, these are all going to be in SI units. They're going to be in meters. They're going to be in kilograms. They're going to be in seconds. All right? So we have to think about units that are in these terms. The reason why we do that is because it makes the math so much easier. All right? If we can just convert everything to basic SI units, you'll never have any inconsistencies. It'll be nice and good. All right, so a milliliter, of course, by definition in SI units, is centimeters. What's the exponent for volume? Cubed. Right? Centimeters cubed. Right? And a liter is what's called a decimeter cubed. And that's 10 so a decimeter is 10 centimeters. Right? And that should make sense. How many milliliters are in a liter? 1,000. Okay? So there are 10 centimeters in a decimeter. Right? We'll go back to dimensional analysis just in case this is confusing, but there's 10 centimeters in a decimeter. There are 3 factors of centimeters, so you have a dimensional conversion of 10 times 10 times 10, 10 to the 3, which is 1,000. Okay? So a liter is 1,000 milliliters. A decimeter cubed is 1,000 cubic centimeters. All right, and then the proper unit that we use, and again, liters are fine. We'll use liters, but occasionally we'll want to enter convert. And of course, that is meters cubed. And now let's do a little test here. Okay, so we have milliliters and liters gives us a factor of 1,000. How many decimeters are in a meter? It's a tricky one. Does anyone know what the deci means in Latin? 10. So there's 10 decimeters in a meter. So it's another factor of 1,000, right? There are 10 decimeters per meter. It's decimeters cubed, so it's 10 to the 3. All right, so a meter cubed is 1,000 liters. All right, it's not a particularly useful unit. That's why we switch to liters typically. We talk about liters because there's not a lot of things that are 1,000 liters except for like swimming pools and vacuum chambers and things like that, or plots of land. Okay, so we can define a volume. All right, that doesn't seem that interesting, but we'll find that it's quite a relevant number to think about. Now, I want to define, there's one more thing that we can measure about the molecules in this box. Now, who here took physics with Poplawski? Most of you, okay. What would Poplawski say about these balls? What are they doing in the box? Yeah, they're moving. Right? They have some sort of inertial right in their frame of motion. They're relative to our perspective. Right? From our frame of motion, we see these atoms potentially moving. They might be frozen, but obviously they're not frozen. We're going to think about this like a gas, right? So if you think about a gas, these atoms are moving, right? So they all have velocities. Right? So we can theoretically think that maybe we haven't really decided how they're moving yet, but you could say, well, maybe some are moving in this direction, some are moving in this direction, right? And so on and so forth. Okay? So we have these massive particles moving through space at some fixed velocity. Maybe it's random, who knows? Right? But at some velocity. All right. So now let me ask you this question. Let's say you have a mole of particles in this box. Now I could write number 3 here and say measure the velocity. Would that be a practical thing for us to do? We had 10 to the 24 atoms in there. Would you want to go measure the velocity of every single one at every time point? No, probably not, right? So velocity is not a useful number for us. Right? Certainly they have velocities, but Newton realized that velocity is not a particularly useful unit to use because, for a couple of reasons. One is that it's really hard to measure the velocities of everything. And the most important thing is that the concept of velocity is not a conserved quantity. What do I mean by that? what that means is that when two, maybe you remember this and so maybe instead of velocity, let me think about this instead. So in physics, when two things collide, all right, so you have an object, you have two balls that come in and hit each other, okay? One's moving at one velocity, and the other one's moving at another velocity, all right, towards it. And they collide and they bounce off each other, all right? What you find is that the initial velocities of those two balls don't necessarily equal the sum of the two velocities of the balls after the collision, right? The velocities change. They're not always conserved. The sum of the initial velocities are different than the final velocities after collisions. And Newton figured this out because he literally did that. He took a bunch of balls or something and made them hit each other and stuff, and he measured very, very finite, very, very carefully the velocity and the motion of every single ball in this system, and then plotted the velocity of all the balls as a function of time and showed where the collisions are. And he shows that the velocities change, they're not conserved. Right? The term conservation, conserved, is not really well defined yet, but we will define it. Right, but he shows that. But what Newton does figure out is that what is conserved are the momenta of the particles. Right? So the momenta of the particles is the velocity of the particles times the mass of the particles. Right? So imagine, I'm just going to erase two balls. I'm just going to kind of zoom into this region right here. Right? And imagine that we have two balls, or two of our atoms, colliding with each other. Right? And one of them has momentum m times v1, m1 v1, and m2 v2. Right? Remember, momentum is mass times velocity. Okay? And so these come in together, and then they bounce off each other. And they bounce off each other with some new direction, like this. And it would be m2 with two new velocities, right? The velocities of each of them change. Right? They have v1 prime and v2 prime. And what does Newton tell us about the sums of these? Well, Newton tells us that m1 v1 plus m2 v2 is equal to m1 v1 prime plus m2 v2 prime. The sums of the velocities are conserved. Right? That's just Newton's third law, right? Every action has an equal and opposite reaction. Right? All that means is that the momenta are conserved. Right? That you always have an equal and opposite response to your impact or whatever event happens. And that's just a restatement of this idea, conservation of momentum. Okay, so velocity is no good, but momentum might be useful. But again, we come across another problem. The problem is now we have to measure, if we have a mole in there, 10 to the 23 momenta. No one wants to do that. Well, maybe Pawlowski would like to do it, but I certainly don't. I know you guys don't either. Okay, so we can't use momentum. We can't measure momentum. And as we'll see, momentum was not a particularly useful unit for us to use anyway. Certainly once you have a lot of particles in the way. So we have to come up with something else that is, one, conserved, and two, something that we can measure that's a macroscopic property of the box. Okay? Something that is not really a function of each atom. It's just a macroscopic number, something that defines all of the atoms and their motion. All right, so what does Newton ends up realizing that when he collects all this data, that there's another conservation law that he finds. He finds that, and actually he gets it wrong, it wasn't figured out until the 1700s, the numbers are right, to get the numbers right. Newton was off by a factor of 2. That if you square the velocities, you get the same conservation. So mv1 squared plus mv2 squared is equal to that. I'll just add some zeros to it, or some squares. Right, so if I square the velocities, this still applies. Okay, and he gives this name. What they realize is that this number is a really nice quantity to use, and they give it a very special name. Does anyone know what mv squared is proportional to? What do they call that? maybe if I add the correct number to it, the correct factor, they later discover there has to be a factor of 1/2 here. Does anyone know what 1/2 mv squared is? Does anyone know what they call that in physics? I thought I heard it. Kinetic energy. It's an energy. All right, we'll look at the units of that in a second. All right, well, think about the units of energy in a second. All right, but you can measure the energy of it. The thing let me say about this. The thing that Newton realizes is that, one, energy is linear. Okay, so every particle has 1/2 mv squared. Imagine all the particles are moving the same. Right? They're all identically moving around. They're all identical. The total energy of the system is 1/2 mv squared summed over all the particles. So 1/2 n mv squared, if you will, for n particles. All right. So, and the question, of course, we'll have to figure out is how the hell do you measure energy? But the nice thing is energy is this nice additive number that describes the motion of all the particles in the box, right? Sum all the kinetic energies up and you get an energy, one number. Right? So what we're going to do for this box is we're going to set the energy of the box. We're just going to fix the energy. Now, the question, of course, is how do you do that? We'll come back to that in a second. Let's just write down this. Let's talk about the variable here. All right, and the energy I want to focus on in particular, this is kind of a traditional term for it, is what's called the internal energy. Right? It's the total energy content of the box. All right, so our variable is called internal energy. And the letter we give it is U. It's a very traditional term for it. It has nothing, I don't know why it's U, it just always has been. What are the units for energy? I heard it. Joules. Joules, thank you. Joules. What are the SI units of joules? Let's see if we can figure that out. Right, that's J for joule, sorry. Let me write that. Joule. J. Okay. And what are the, of course, joule is just a letter. All right, so we should convert it back into the units of SI units. Right? And all we have to do is say, well, the energy is just m times v squared. So the units of joules are very straightforward. You can just read them off, right? We have a factor of kilogram. By the way, whenever I write triple equals there, that means equivalent to. It's just kind of one of my notations. So there's a factor of kilogram in there. And then there's a factor of velocity squared. What are the units of velocity? Yeah, there we go. So it's kilograms meters squared per second squared. Okay. Right, and often we use joules per mole, right? You can also use joules per mole. Right, we'll introduce other there are other types of energy, other units of energy that we'll talk about as we go along. Because the joule in particular represents a very specific kind of energy. What is that energy? Well, we just derived it from the mechanical motion of particles, right? This is what we call mechanical energy, right? It's the classic form of energy. This is when Henry Joule himself, the way he defined the joule and discovered the idea of energy is he literally, he had like I'll explain the experiment eventually, but it basically from analyzing the motion of a wheel, like a spinning wheel that is moving in some material, where the energy of the mechanical energy of the wheel is being transferred into the material as heat. Right? I also mentioned this term heat. We didn't even talk about that yet. Right? But so this is mechanical energy, and it's a good unit for energy in general because it's, of course, all energy has the same units as we'll see, but joules are good context for mechanical energy traditionally. But there are other types of energy, right? Right? Obviously, these are not being lit. These are not energized by mechanical energy, right? We run an electric current through these lights, which excites the atoms in the gas and which emit radiation, right? So the energy in here is electrical energy, and the light that it's emitting is also energy, and it's light energy, which is also electric energy, as we'll learn, right? So there are different types of energy, and we'll go through those types of energy, but the important thing is that all energy is the same. Regardless of the context, you can always measure it in joules. Right? Well, it's a very subtle point, but we'll come to it. Okay, so it turns out this is almost everything we need to define the box. We know something about the particles in it, and we know something about the box itself, and we know something about the energy. And you might be thinking, well, I've got a box in my room. It's really hard for me to measure the energy of the particles in that box. Right? It's not really easy to, let's imagine your dorm room is the box instead. Right? It's not really easy to measure the total energy of that box or your room, right? But you can feel the energy of the room on your skin. Right? Right? And how do we qualitatively or quantitatively measure that energy, right, in your room? You know the energy, the internal energy of your room all the time. What unit do you use to measure that? Think about all the little gas particles bouncing around in your room. Temperature. Temperature. Right? How does temperature get here? Right? I haven't specified temperature at all. Right, so we have to think about, well, right, so there must be some connection, right? The idea is that the more these, right, this is kind of the classic way you think about temperature. So temperature represents something about the average motion of the particles. And we'll see that that's exactly what temperature is. But there's nothing here that tells us anything about what a temperature is. How do we convert between internal energy into temperature? They have very different units, right? Kelvin has nothing to do with joules. Celsius has nothing to do with joules. But you have this intuitive sense that they must be related to each other. Okay, and I want to show you today, very briefly, very, very simple, to show you how temperature is defined. All right, that we're going to end up using temperature quite a bit. And it leads us into some of the more key, kind of the key points of kind of the basics of this class. Now, temperature is a really important number, but there's nothing here that defines temperature. We have to think about what temperature means. Okay. So let's think about that for just a second, okay? So far we have particle number, volume, and internal energy. All right, one thing that we haven't also figured out, are these related to each other? For instance, if I change the volume, does the energy change? If I change the number of particles, does the energy change? Well, we can answer that question right now. All right, so we'll worry about the volume in a second. Let's think about particle numbers, right? Each of these particles have some kinetic energy. All right, so I put one particle in there, in the box. All right, so I make n equals 1. The energy is mv squared, 1/2 mv squared. Now I put two particles in the box. What's the energy? 2 times that. Put 3 particles, it's 3 times that, right? The energy is a function of the number. Right? So not all of these are necessarily independent. Not only that, right? It's also dependent on the mass too, right? Because the kinetic energy is proportional to the mass. Right? So if we change the mass of the particles, we're going to change the internal energy of the system as well. Right? So there's some discrepancy here. That these are not all equal, if you will. Right? Internal energy is dependent on the other things that we've used to define the box. What we'll see also is that volume, or rather energy, is dependent on the volume. So let me ask you this question. Let's go back to general chemistry. You have a balloon. It's a formable material that you can fill with gas and seal it. Okay? And let's say you fill it with a mole of helium. Okay. let's do that really quick. So think about that, right? So you fill it with a mole of helium. What does the balloon do? Well, initially when the n is equal to 0, the balloon is limp and lame and not doing anything interesting. What happens as the balloon fills? The volume increases. Okay, so now let's say I set now the volume of I put a whole mole in there and I close off the balloon, all right, some volume. And then what I do, let's say it's a really, really strong balloon, it's not going to pop. I squeeze it, I bear hug it, right? What happens to the balloon in terms of our variables? Does the number of particles change when I squeeze it? No, obviously not. None of them have leaked out. Has the volume changed? Of course it did. I just squeezed it. I've made it smaller. But what do we call, so when you think about now, what has changed in that balloon when I squeezed it? I've reduced the volume by 2. What do we say in chemistry has happened to the gas in that balloon? What other variable do we talk about? Pressure. The pressure has increased, right? As we're going to find out, pressure, and it's not going to take us long to get to it, but it'll take us a little bit of time to get the math to there, but what we're going to see is that pressure is the response of the system's energy to changes in the volume. All right? We can set the number of particles and we can set the volume, and then as we change the volume, the pressure changes, but but what we'll find is that pressure has something to do with the energy. So as we start to decrease the volume and increase the pressure, what happens? Well, there's less room for those particles to move, and the particles now are hitting the walls harder. They exert more force against the wall and increase the pressure. I just said that they exert a force harder against the wall, right? That's it exerting energy, right? That's it transferring energy into the walls, right? It's pressing against the walls of a force. It's doing what we call work, mechanical work, against the walls of the balloon. So pressure is just the response of the system to changes in volume, right? And that has something to do with energy. So when we change the volume, we change the pressure, which means we're changing the energy of the system. So this is not an independent variable. It's a function of the other variables. All right? So what I could really write this as is a function. Right? I could say that the energy of my box is a function u that's a function of the volume and the particle number. Right? Maybe there's multiple components in there. There could be multiple n's, right? Maybe you have oxygen, you have a mixture of things too, right? But it's a function of both of these numbers. Once again, we have nothing here about temperature yet. We have to think about temperature. So total internal energy has something to do with volume and number. We have terms for these variables, right? So these inputs, V and N, these are called extensive variables or extensive properties, right? They effectively define the system, right? The box is defined by the volume and the number of particles in it, right? Those are the only independent variables for now, right? And U, the energy, is what's called an intensive variable, which is kind of like a response, right? It's a output given the input. It's a property. It's a property that depends on the extensive variables. Now here's an issue. This is an incomplete picture. So let me erase this. Let me just erase, I'm not going to erase it, sorry. I'm just going to erase this right here. Because this is an incomplete number of variables. There's more variables than this. And let me explain why. Right? I'm saying that the energy of my box is a function of the volume and the number. And I'm assuming that the masses are all the same. Right? We're going to worry about mass. You could say it's a function of the mass, but we won't worry about that. But it doesn't tell, right? This doesn't tell you anything about the velocities. Right? Remember I said that the energy is specified by some speed. Right? There's something that has to determine those velocities, and v and n don't tell you anything about that. Let me explain why that would be, right? It doesn't matter whether you have 100 particles or 10 to the 20 particles in a box at room temperature. They all move exactly the same, right? A gas, no matter the size, functions the same. All those gas particles are moving the same at fixed temperature, right? And then of course volume doesn't affect it either. As you start to compress this balloon, as long as you don't change the temperature of the gas inside, they're still moving the same, right? I'm continuing to use this idea of temperature. Right, so this is a fundamentally incomplete picture. We're missing something here because we haven't determined anything about the dynamics of the particles. Right? We just know something about how big the box is and how much they're moving. The energy has something to do with that, but there needs to be something here that tells us about the actual motion of the particles in the box. All right, so we have to figure out what that is. Yes, ma'am. Go ahead.
So when you're talking about like the velocity, it's the same at any temperature, you're saying? Like it stays the same if you're staying at the same temperature.
Correct. So just think about, right. So the idea is this room and that room over there, let's assume that they're both sealed. All right, I sealed the doors. So the ID card office is sealed and this is sealed. And I set the thermostat to 25 degrees Celsius in both of them. All right. The average velocity of the air here and there is exactly the same.
So, but it's like, so my question there, I guess, is like, since they're colliding with each other over and over again, how does the velocity change considering like?
That's a great question. We'll come back to that. So what Monica asks is that the thing is that these atoms and stuff are moving constantly, and they're constantly changing their velocities. That's a good point. And in fact, what we'll find is that some might not be moving at all, and some are moving really fast. Right? So there's like the distribution of velocities. We have to use a little statistics to answer that question. Okay, so you're exactly right. The point that you're making is 100% true, but only at the limit where you can count the particles, small numbers. Right? Imagine now, so think about it this way. Does anyone, who's taking statistics in here? All right, anyone tell me what the central limit theorem says? Does anyone remember that from statistics? All right, so what does the central limit theorem say? Central limit theorem says that the mean, that for a properly chosen sample of a population, the mean and the standard deviation of the sample is equal to the mean and the standard deviation of the population. So let's say you pick out 100 random atoms out of this box. There's 10 million in there. You pick out 100 at random. You ask it what's its velocity. All right, and you measure the mean, the average, and the standard deviation, the variance of that number. And the central limit theorem says that if you pick those randomly and appropriately, then the average that you measure for those 100 is the same as it is for the 10 million. Right? This is the whole point of political polling, is that you can call 100 boomers and get some idea about what 300 million people will do when they're voting. Right? Of course, that doesn't work very well because I don't know if you guys know this, Quinnipiac University is one of the major places for political polling. And they don't teach them particularly good statistics, and so that's why they're always off at Quinnipiac. So anyway, I digress. So there's something about statistics that we're going to have to think about. Let me drive this point home a little more. Any other questions while we're here so far? Okay. How much time we got? 10 minutes. Okay. So we'll come back on. Hopefully we'll get, I don't know if we're going to get to the point where we're going to have temperature today, but let me come back to Monica's point. Right, I want to have this idea that we can't measure things, so we're going to have to take statistics. We're going to have to do statistics on this system because there's no possible way for us to do any sort of measurement of individual energies and sum them up. That's impossible. Right? So especially for a normal macroscopic system. So we're going to have to do something clever. We're going to have to take statistics. And I want to drive that point home before we go. All right, so I'm going to change pages. If yell at me if you need any more time to write stuff down. I don't think you should. Okay. So let's make a really, really small box. All right, I'm not going to draw it as carefully as I did last time. I'm just going to kind of sketch it. All right, and inside of this box, it's a tiny little box, microscopic box. We're going to put 12 atoms in it. All right, and I'm going to do some special things with these atoms. We're going to put in the middle of the system, and say the center of mass of the box, a particle with +2 charge. All right, so we're going to add some charges here. All right, so this is like a cation. All right, and there's going to be some number of atoms around it. And what we're going to do, this is not really relevant, we're going to think about these atoms being connected by springs to the center atom. So on the right edges, there's going to be 2 -1 charges, 2 anions, if you will. Those are -1s that are connected by springs. And then there's going to be a series of neutral atoms that are connected by springs to the center atom. All right, so here's my little spring. There's an atom here. There's an atom here. There's an atom here. There's an atom here. Atom here. Atom here. Is that the right number? I have too many. I'm sorry, guys. So I said 1, 2. How many do I have here? 1, 2, 3, 4. Oh yeah, that's right. There should be 4 on each side of the quadrant. Sorry. So let me erase that. 1 too many. Yeah, there we go. So let me just clean this up a bit. All right, and these are neutral atoms in orange. All right, so I'm just going to have 4 kind of spitting out on the side here. Okay, so I've got my 4 atoms. They're connected to springs to the one in the middle. Okay, so, and what I'm going to do is I'm going to fix my reference point, right? I'm going to sit on that +2 atom at the center of mass of the system. I'm going to stand there and I'm going to watch the motion of all the other ones around me. So this atom, the +2 is going to be fixed. All right, so we're going to fix our axis system, our frame of reference, to the cation. All right, so you can kind of say that I'm sitting here. Here's my eye. I'm like looking at the atom sitting on this +2. All right, so we're not going to be able to quite understand this completely until next semester, but if you took, hopefully if you took mechanics or waves, you talked about springs and oscillators and physics, you might have this idea is that when you have a system of independent particles where they're all moving randomly, right? We're going to have them all moving in different directions and stuff. You can always define a set of coordinates called normal modes. A special defined coordinates of motion called normal modes. And these are motions that preserve the center of mass, all right, which means the +2 atom is not moving. Center of mass preserving. When we talk about the vibrations of molecules, this will become very important. The center of mass preserving. So what we're thinking about are all the possible motions of all the atoms bouncing around this +2. All right, and there's a really easy formula for it. For n atoms, there are 3n normal modes. Okay, I'm just going to draw a couple of them. All right, I'll show you what it means. These are collective motions of the system that preserve that +2 sitting right in the middle. So the +2 is not moving. There's no net velocity or force on the +2. All the forces of all the other atoms are canceling it out. You can always make this transformation. It's what Einstein told us with the equivalence principle in special relativity. You can always define a frame of reference where the object you care about is not moving. It's stationary in your frame. So we're going to define a frame of reference where the +2 is sitting and not moving and everything else is moving around it. Einstein tells us that we can always do that. So here are some examples of some of the normal modes. So maybe let me keep these colors constant. Sorry. Right. So one motion that can happen is that and I'm just going to kind of roughly sketch this now. Relative to the cation in the middle, all of the atoms move away equally. Right? So I can draw this one moving away, this one moving away, this one moving away, this one moving away, this one moving away. Right? They can all move away. Now imagine you're in this box, and all the atoms are pushing away from you. Right? What is changing in the system? Well, what you're doing is you imagine the box is just kind of the shell wrapped around all these atoms. You're pushing that shell apart. Right? You're increasing the volume of the system. Right? So this is what we call mechanical work. Right? You have a net motion of atoms pushing the boundaries of your box, or pushing against the boundaries of your box, and making this kind of shell of atoms stretch and get bigger. Right? This is it doing mechanical work against the system. Right? And so the change in volume here is not equal to 0. What does that mean? Well, that means that the change in energy is not equal to 0. Right? It's doing something physical. Right? This is kind of what you can think of pressure in some ways. It's somewhat related to this. Right? So imagine now this happens in our box. You're going to now let's say for instance now that this box, you can make this box, but you can't quite observe each atom moving. It's kind of hazy, right? Like you're like tripping on shrooms and everything's kind of moving around. You don't quite know where things are, right? So I'm going to kind of, right? So think about you have this like hazy magnifying glass that kind of blurs over the motion. Okay, so you can't see the individual atoms moving, but you can see the effects, the macroscopic effects, right? And so here you would notice this, right? Even though you can't see all these atoms moving away, they're moving very, very fast. Right? The time scale, I'll just write this, the time scale of this motion. So imagine these are like little springs moving back and forth. So the time scale of an atom moving back and forth with respect to another one, delta t, is around 10 to the minus 15 seconds, a femtosecond. All right, so these atoms are bouncing back and forth at 10 to the minus 15 times a second, 10 to 15 times a second. All right, so you can't see them move, but you can see the response. Right? And this response is macroscopic. It changes the volume. So what you're going to see is that if the system's moving along in this path as you observe it, it's stretching the box. Right? It's a macroscopic effect. Okay, so let's look at another one. Again, I'm just going to write this very roughly because I'm running out of time. So I'm just going to put a minus and a plus in here. Now what happens instead if the little orange atoms are colliding with each other? So they're moving and bouncing off of each other. Oh, I have this wrong. I'm sorry, I have the arrows wrong. I apologize. So imagine now, sorry, I have the ordering of these wrong. So imagine that these two are bouncing back and forth. The negative charges are bouncing like this. Right? And then you have the other four atoms, how do I have this drawn? Bouncing against each other like this. This is allowed. Okay, so the atoms are just kind of colliding with each other around in a loop. But what has happened is that if you think about this motion, again, you can't see it, but do you observe any effects? Well, what happens is that when these bounce, these two negative charges bounce, you've moved, right? You have some distance between them, r, and then when they collide, you're at some new distance between them, r prime. Right, so I'll draw the little atoms. Imagine now they're right here instead, right? Right, so the distance between the positive and the negative charges are changing when these collisions are happening. Right? So the distance between, you're extending basically the displacement of the electric field that's created between the attraction of the negative and the positive charges. This is called, so what changes macroscopically in this system when you average over all of these little collisions, but where the negative signs, or the anions are moving, have a net motion away from the center that are equal and opposite. Well, this means that the system has a dipole moment. Right? The dipole moment, which is roughly the vector between the positive and the negative charge, and the magnitude of that vector is the distance. So as these atoms are moving, you're changing the dipole moment. You have a change in the dipole. So dipole, we always write mu. Right? So mu, which is equal to roughly, in this case, it's proportional. I'll just write this. It's roughly equal to the distance times a constant. Right? And that's changing. Sorry, delta R. Right? So the length of them is changing, and the dipole is changing. What that means is that when you measure the dipole moment, or the polarity of this mixture, it will have a net polarity. All right? So this is a macroscopic effect as well. You can measure this. All right? There's one more motion I want to show you, and then we'll finish it up. And we'll continue on next time. Just take me just a second. The final motion I want you to think about is the motion where the atoms basically are just colliding in a circle around them. There's going to be a number of motions that look like this, where basically the atoms just kind of do a conga line and collide with each other in pairs. Right? They just bounce off of each other in pairs. Like this. Okay, so if you think about this happening lots and lots of times, what you get is a helicity. It's rotating. Right? This is kind of like a rotational motion, right? This atom collides with this one, that one collides with this one, that one collides with this one, that one collides with this one. Right? They're starting to rotate around this, right? There's some net angular momentum. Right? So there's some velocity of the motion in this direction. There's a circular motion. Right? The volume is not changing here because it's right, you're just rotating a circle, right? The radius of that circle is fixed. You're not stretching it, you're just rotating it. So delta V is equal to 0. And because you're not stretching it, delta mu, the dipole moment, is equal to 0. So the volume's not changing, the dipole, which would be like the electrical energy of the system, is not changing, the number isn't changing, right? So this therefore means that the energy does not change. Right? There are many, now imagine you have 10 to the 24 atoms. There are many motions like this where they just kind of collide and bounce around. The volume doesn't change, the dipole doesn't change. Right? This is work, this is electrical energy. There's no energy change. Right? So these are the motions that you want to think about. These are these random motions. This is the sample you want to collect. These are these random motions. They don't change the system at all, but they're happening constantly. And they average away. They just disappear. These are averaged away by statistics. So when n goes towards infinity. All right, so as the system gets bigger and bigger and bigger, there are more of these motions and they don't affect the system at all. They all average out. Okay, so we have some properties that microscopic motion leads to changes in energy, and then we have a set of motions where it does not. All right? Think about this. This is just random collisions of atoms. Right? This is what's going to define our system. We're going to average over these, and we're going to find a way to determine temperature through this process. All right? The speed and the intensity and the change of this as you change the internal energy of the system, the change of these motions and this averaging is what defines temperature. Okay? So next Wednesday we'll come back to that and we'll actually be able to create a thermometer for the first time, okay? All right, you guys have a good weekend.
Is it okay if I ask you a question?
Yes, ma'am.
I just know you were rushing, so I didn't want to.
Yeah, go ahead, please do.
So at the end, for the last part, so you were talking about how like the velocity or the change in velocity and the change in energy are both, or in the dipole, there are not like they're not right, or there's none. So
I'm sorry, I don't know what you mean.
sorry. So like
So in this case,
yeah. So for these two, since the energy, or sorry, the velocity and the dipole are both zero, right?
Yes.
Thing.
Yes.
But then what about how when we were discussing like the overall energy, like there's other variables.
Right. So my point here is that so what we've done here is we have 3 different types of motions. This one defines the internal energy in terms of work. Right. So this tells you something about the work that's being done by the system with its energy. It's a type. It's like you think of this as a portion of the energy of the system. It's these little mechanical motions. Right? There's also electrical motion that causes changes in the dipole, which introduces changes in energy. And then there's also this motion. Of course, there's energy in the system. The things are moving.
So it's not
But-
it's
but-
so constant. It's like,
But it's constant and it all cancels out. So it doesn't affect the energy at all.
so then my question is, this might be like silly, I guess, but for this one, like there's no like vibration, right? Like it's only going out. Is it going back?
Well,
Like, do
they're
you know what I'm saying?
oh no. So the important thing is that they're on springs. So they're oscillating back and
they're
forth.
oscillating.
Yeah, think about them as little slinkies. That's right. We'll come back to that idea later. But the idea is that there are properties that when you imagine you have 10 to the 24 atoms, there are properties that you can determine that there are changes macroscopically. Here's volume, right? You're pressing
You
against
see
the
it,
box.
it's
You
kinda
see it physically.
Yeah.
You see it stretch here. You measure the voltage, the charge distribution. You get a current, basically,
Because
from
of the
this.
dipole.
Right, because of the
Okay.
dipole, or you put it in an electric field and you see it moving or something like that. You can
Yeah.
measure that very easily. But there's an entire set of motions where it doesn't affect anything at all. Basically, these are free, right? Because the energy doesn't change. They're just freely available to do.
That makes sense.
And so we won't measure any of these, and what we're going to do is, to define temperature, is we're going to take all of these motions and average them together, and that'll give us some sense of the thermal energy of the system, the heat. So ultimately what we're going to do is that when we average all of these, this will give us a definition for heat, which gives us temperature eventually. Okay, so these motions that don't change the energy, don't change any of the internal parameters,
So then
are the
my-
things that define the temperature.
So then how are like which formation you're like what you're seeing, how is that like defined? Like what, like when do they follow this, when do they follow that?
They do all of, well,
They
we'll
just
we'll
do-
say
and then you're
that all of
averaging
it
it
is
and
happening all the time. That's the
Okay.
assumption we're making,
So when
is
you
these
have,
are all
like-
happening so much that we can't measure them individually.
So
There's
the-
just, they're basically infinite.
When you have like a higher temperature, like some of these are occurring more, like you would.
They're all occurring more.
They're all just.
They're
like-
all occurring more, but the point is that we can observe macroscopic changes in some of them, but other ones we can't.
Okay.
Right? So
I'm sure it'll make more sense
Yes.
also when you.
let me put it this way. So this is ultimately what we'll find is that this results in pressure changes.
Yeah, that makes sense.
This results in I don't know, current or electrical energy, electrical
note of that.
voltage
That
maybe,
actually
or
makes a
something
lot
like
more
that,
sense,
or
yeah.
not voltage. I don't know what you would call it. Polarization, I think, is the term that a physicist would use. So polarization, right? You're creating an electric field, right? So you would notice a macroscopic change in pressure, a macroscopic change in polarization, but then you have the rest of the motions where nothing changes at all, delta U is equal to 0, but they're still always happening all the time, right?
Mm-hmm.
And that's heat, as we'll find out, right? That's a different type of energy. I have to get out of here, I'm sorry.
Thank you.
You're welcome, I'll see you Wednesday. I'm sorry, I'll be right out of your way.
Oh, you know what's actually quite funny because you were mentioning Poplawski. I'm Poplawski's learning assistant this semester.
Oh, okay.
And he loves to talk about the hierarchy of science, like the classic one that you're talking about.
Yeah.
And so I sent him the paper that you assigned
Oh,
us
good,
to
good, I
read.
hope he likes it.
Will I be able to log back on here?
Yes.
I'll let you know what he says.
Yes, you will be able to. If you just touch the keyboard, it'll ask you for, actually, so do it right now. Touch the keyboard really quickly, just a button. And then switch user at the bottom left.
Yeah.